Good welcome to the 5G Technologies and Business Insight webinar from us here at Telecoms Academy. Now we'll just do a quick introduction to who we are and what we do. If you've got this far in terms of registration and so on, you've probably got a pretty good idea of who we are and what we do. You might have even attended some of our training programs. Telecoms Academy is a training organisation which sits under the sort of Informa, the Ovum brand. And the structure of the company is that we've got a couple of different schools that sit within our own house. So we've got telecoms management, advanced communication technologies, and distance learning and such like. I think something that might be relevant, or one of the courses that we're launching this year, which might be relevant for those of you attending this session, is in fact a 5G mini MBA. Again, some of you might be familiar with the standard MBA and some of the other flavors of MBAs that we do, but we're launching now a 5G focused mini MBA that really, it looks at the technology, but it looks a lot at the business. How are we going to make a business out of 5G? And I think that's the big question everybody has these days. We've got there's a course coming out at the beginning of May in Dubai, and I think again in June also in Dubai. And contact the sales team or get into the website to find out more details about the exact dates and so on. For that, I should probably also mention that we do like a really focused 5G course, just a 2-day program that really looks at, what do we think it's going to be in terms of technology, how we're going to make it into a business, how we're going to sustain it, and we talk around some of the use cases, the applications that 5G could be used for as well. So there's some contact details at the bottom there. Again, this will be the final slide that I show you, and you'll be able to get in touch with the training team and such like. But let's get on with the main topic here. Right now, defining 5G. Well, is that an easy thing to do, or is it a difficult thing to do? Because at the moment, it's still pretty unfocused in terms of what the overall thing will be. I mean, we know it will be better performance, it'll be high speed, low latency, all those kind of the usual things that you would see whenever we talk about 5G. But I think there's a couple of key areas that we could probably focus on in terms of the overall 5G system. And I think maybe the one that's attracting a lot of attention at the moment is, should we say, at the top end of the stack. So in terms of, applications, services, business integration. So what are we going to use it for? And I think that's one of the interesting things about 5G is, in times gone past, the previous technologies, of course, the current one that we have, the 4G LTE that we have, and the 3G, I think what we've done in the past is we've kind of invented a technology that has a certain level of performance, and then we've tried to think of things, applications and services that we can use this technology for. But it almost seems the other way up with 5G, that there seems to be an awful lot of work, a lot of effort gone into defining what do we think we could do with a new technology, and then on that basis trying to define what the technology should be. So what should the core network look like? How should it integrate to business? What different radio access techniques should we use to meet those performance requirements and so on? So it's very much a top-down approach. Think of an application, then try and think of a technology that can solve the specific problems that these applications have. And there are many different use cases. I'll talk about a few of them in a moment or two. But of course, there's the video. There's high-speed internet. IoT, I think, is going to be quite a big one. And then all of the smart applications, smart city, smart home, smart industry. Vehicle to vehicle or vehicle telematics. There are many different applications that could benefit from a service like 5G. With its high capacity, perhaps low latency, and so on. Now, given the I guess the very broad scope of different kinds of applications that we're going to have, and of course many of those applications have very different performance requirements. When you look at the throughput, the speed of the connection, and the latency, and so on. A lot of these applications have got very diverse requirements. So actually building a network that can deliver those is quite a complex thing. Now, some of that is going to be addressed in the bottom layers of the stack, so the actual infrastructure itself. I mean, it's primarily a wireless network, of course, but what we're seeing coming out of 3G and 4G is that there's this requirement to be able to interconnect with non-3GPP networks. Okay, so this means, of course, wireless LAN and maybe even some fixed networks as well. So it seems highly likely that 5G should be entirely interworkable, compatible with so-called non-3GPP or non-mobile technologies as well. But we tend to focus on the wireless aspects here. So, we've got to think of new radio interfaces that can support low latency, high capacity. It's got to be extremely efficient in terms of the way in which it uses the radio spectrum. And when we start considering things like the IoT applications, well, depending specifically on the IoT application, there are requirements for low power, short or long range, maybe broadcasting technologies. And it does seem kind of inconceivable that there would be one radio technique that could solve all of those problems all at the same time. So it seems quite likely that what we'll see out of 5G will be multiple radio access techniques, multiple physical layers effectively. But then, of course, you've got to be able to control those. You've got to understand what application is making a connection from the access network, and then configure all of the domains. So, this hyper-connected infrastructure. But also, when you get back up into the core network, it's understanding what those the quality of service requirements, if you like, and how we provision and configure all of the network components as efficiently as possible. Now, we'll say a few things about this. We'll have a very quick look at the core and the access network in a moment or two. But one of the key technologies is this aspect of virtualization. Okay, effectively simulating the network functions on a common off-the-shelf platform, which gives you access to a lot of configuration and gives rise to this idea of being able to create so-called network slices for different kinds and styles of applications. And there's also an opportunity here to expose the capability of the operator, and there's an interesting term here, network as a service. Because you can imagine somebody like the auto industry. I mean, they clearly have a communication requirement in terms of, telematics and vehicle function, entertainment, wherever that might be. But vehicle companies don't want to be mobile operators, but they maybe want the mobile operator function. So what we have to do is to create an infrastructure that can expose the network capability to the relevant industry and provide the right kind of services in the right places for those various industries. So when you go back to the top of the stack again and you consider the range of industries that may require these connectivity functions, the operator has to produce a core network which is very easily provisionable and configurable for all of these diverse requirements, and of course choose the right network functions. And when you get down into the radio access layer again, making sure that you're connected in the right way with the right requirements, whether it's a low power requirement or a high speed requirement, or whether low latency is required. And doing that is going to be quite a challenge. Certainly today's technologies, we're a step or two away from having an easily configurable network in this way. I don't know if this is a good analogy or not, but I don't know, I quite like it. But you can almost imagine at the edge of the network here, almost something like an app store for the connected vertical. So all of the industries up here, they clearly understand what their communication requirements might be. And it may be the job of the operator to create something like an app store whereby we can just connect our industry, our requirements to the back end of the network, and have the whole system configure or be able to decompose and understand what the communication requirements are and create a configurable layer or a network slice on an end-to-end basis. So from the company servers that sit up there in the wherever they happen to be. So you got a big vehicle manufacturer up here with their own network, their own servers, because they're clearly interested in being able to deliver a service directly to their customers, the people who are buying the vehicles and so on. But they want to be able to make use of the communicating platform, which is the operator's network. So we have to be able to say whether the particular application requires low latency, high speed, and so on. So it's a very big picture at the moment. It's a very cloudy picture, I suppose, because at the moment, we're just going to draw a little cloud around these things and say, right, okay, there's a network in here with a bunch of virtualized functions which we can configure at quite a deep level. So it's quite hard to put it, to pin down a proper 5G definition. And I don't think the network's going to look like a 3G network or a 4G network, where you can actually, there is some sort of single end-to-end architecture that you can draw out and explain every part of it. And I think it's going to be much more, what does the architecture look for this application, and how does the architecture change for these other applications? So it's perhaps a little bit of a confusing picture at the moment. But the start of it all, I'm quoting here from the NGMN, the Next Generation Mobile Network Forum, and they've got a nice document which I'll link to at the end with these use cases. But just a little bit of a history lesson here. Of course, a lot of it comes out of the ITU. Well, most of it comes out of the ITU. And what the ITU are running at the moment is a project, if you like, called IMT 2020. Now 2020, of course, being the year in this case. And the deliverable, if you like, from that particular project will be whatever we call the technology 5G. They've done this in the past, of course, with IMT Advanced, IMT 2000, which defined the 4G and the 3G services, respectively. So this is just another round of that definition. of what this so-called next generation of technology will look like. And what the NGMN have done is they've taken up the project and they've started to say, right, what can we use it for? And these are just some examples of the use cases that they've defined. It says in their own document that this list, if you like, is not meant to be exhaustive. We're not trying to think of everything that we might be using this new technology for, but just some example cases that allow us to use it as a tool to ensure that all of the required capability can be well captured and therefore defined and at some point turned into specifications. So, broadband access in dense areas, so stadiums and indoor environments, shopping malls, airports, that kind of thing. Broadband access everywhere, so between 10 and 50 megabits per second, literally everywhere. So 100% geography would be the admirable aim, I suppose, to get to that. But then you can sort of come to the more specialist applications of high-speed users or high mobility users, massive Internet of Things. Of course, that's going to be a big thing for 5G. I have seen some people quoting that 5G really is all about the Internet of Things, one way or another. But there are some very niche and specialized services that might benefit from this as well. So extreme real-time communications that has a very low latency requirement, things like tactile internet. That will be things like augmented reality, for example. So we'll all be walking around with Google Glass or Microsoft HoloLens with real-time access to augmented reality data, in our field of vision. That's the kind of application that, or one of the applications that might be used for that. But there's a bunch of public safety stuff in there as well. PPDR is often referred to, so public protection and disaster recovery type communications, as well as ultra reliable communications. And we shouldn't also forget traditional broadcast type services as well. So it's interesting that they created this case. This is what I mean by when I talk about the top-down approach that 5G has taken, because this is one of the very early documents related to 5G, and really just talks about what are the things that we're going to do, what are the things that we might be doing with this new technology. Now they're taking it a bit further, and of course I'm not showing you the whole levels of detail here, but they take it a little bit further and say, right, for each of those use cases, what would a typical user experience be, both in terms of the the upload and download speed of the connection, the latency, and what the mobility might be like. So this is just an example table, again from the same NGMN document, which has got some pretty terrific figures in here, because one thing to note here that this sort of second column here, it says user experienced data rate. Okay, so these data rates are not, average cell capacities. These would be a per user experienced data rate. So when it says here broadband access in dense areas, so imagine the shopping mall, the airport, the stadium, for example, then what it really means is that you, I, and everybody else in that particular area would receive something like 300 megabits per second in the downlink, 50 megabit per second capability in the uplink, with something like a 10 millisecond latency, which is quite an impressive figure to get to. But when you look at this indoor high, ultra high broadband access, it goes all the way up to like a gigabit per second. Now, I must say, when you consider this is what we might just call sort of enhanced mobile broadband. You might see it written elsewhere as EMBB, something like that. Now, at this point, when I start looking at these numbers, 300 megabits per second, a gigabit per second, I'm going to start asking questions like, well, what are you using it for? What applications are you running on your tablet or iPhone 15 or whatever it might be? What applications need a gigabit per second? Because we're not talking about cell rates here. We're talking about, as it says, user experience data rate. And I don't think there's any applications out there at the moment, no sort of personal applications that we would use on a day-to-day basis for sure, that would need something like a gigabit per second. So unless we start hosting websites and other kind of things from our mobile devices, maybe we don't need that capacity right now. But in 5 years' time, in 10 years' time, this industry moves at a very, very fast rate. So I'm almost certain that given the capability, we'll be able to think of an application that can make use of those services. So we're not going to go through the whole table here. We'll just kind of point out things like the ultra low latency services. So again, things like augmented reality, maybe tactile internet services with like a sub-millisecond latency. Now that's really quite a hard thing to do, because when you start talking about millisecond end-to-end latencies, you're sort of bumping into the laws of physics here. If you think how far you can transmit an electromagnetic wave, for example, in a millisecond, well, it's not very far. It's constraining the geography of the architecture in that case. So you then have to start thinking, well, okay, what are, things like collision avoidance, for example, with vehicle-to-vehicle communications. Then if you want to be serious about those kind of things, you've got to limit the physical geography of the architecture and maybe even start considering things like mobile edge computing, where you bring computing and content power into the access network, because you can't have some distant data center somewhere that will be serving up the content or serving up the telemetry data for collision avoidance. You can't have that in a different continent or a different in a different country. It's got to be localized with the specific application itself in order to achieve these kind of things. So there's a propagation distance to consider here, but also something like a frame structure. Now, some of you will be familiar with the LTE frame structure in terms of its 10 millisecond frame time and 1 millisecond TTI. But even with that current frame structure that we find in sort of normal LTE, LTE advanced, it's difficult, if not impossible, to get down to these levels of certainly sub-millisecond latencies is near impossible to get to. So that seems to indicate there must be some restructuring of the radio interface to meet some of these requirements. Now there is a good document recently released. Where's the number of that document again? So it's an ITU document, and the name of the document has a very catchy title. It's R15 SG 05C. There you go. Really rolls off the tongue. Now that was a document released in February of this year, which defines the minimum requirements for technical performance related to IMT 2020 interfaces. That's the heading of the document. Now, what that document really boils down to is identifying sort of 8 key requirements in terms of capacity, latency, reliability, efficiency, and so on. And it's not a bad document to look at. Again, I've linked to it in the last page that we get to, but it basically says capacity. Okay, we're going to need up to 10 gigabits per second out to the endpoints in the field, and it says again, not a theoretical maximum, and a practical capability, 1,000 times more bandwidth per unit area. I mean, compared to what we have currently, and the number of connected devices, the density of connections that we can support needs to be increased massively as well. If you think of smart cities, for example, and anything that has a power cord or a battery on it is going to have, a 5G modem in it, then the density of electrical and electronic devices in that area will be extremely high. And again, the current technology kind of struggle a little bit to get to those kind of levels and to maintain performance as well. And of course, you've got at the extreme, you've got the 1 millisecond round trip delay. And then this idea of reliability, and it's an interesting choice of words here, but the perception of 5 nines availability or 100% coverage. I'm not quite sure what they mean by a perception of. But nevertheless, that's a target, in terms of building and planning the networks. That's something that will need to be considered. And then, really interestingly, the overall efficiency in this case, very specifically, power efficiency. So, a 90% reduction in network energy use and 10-year battery life for some kinds of applications. And that's quite a challenge. Certainly, chipset vendors out there will be working very hard to reduce the power consumption of their chipsets. And when you're considering relatively maintenance-free IoT deployments, then things like a 10-year battery life might be something which is an important consideration to manage the cost of deploying such a large-scale systems. So I recommend you go and find that document or link to it. Click on the link when we get to the last page and have a read in that. There's a few formulas and such like in there, but it's not too bad. You can miss the formulas out and just read the paragraphs. It's not too bad. And again, this is just another way of presenting the same information, I suppose. But when you look at certain types of application and think about the KPIs, if you like, so we've got connection density, latency, mobility, spectrum efficiency, that kind of thing, then obviously the different types of use cases are going to have differing requirements in terms of those KPIs. So, for example, this sort of scale you've got here, low, medium, and high importance. So this is how important it is for that particular application. So massive machine type communications, connection density, as I mentioned, is going to be a really, really important feature. But when you come to things like ultra reliable, low latency communications, then, well, of course, then the latency and maybe in some cases the mobility become the high importance metrics or KPIs. But it's interesting to compare where we are now, or roughly speaking where we are now, with what the requirements of IMT 2020 are, and that's what this kind of bottom picture shows us. So if we just expand the scale out to, IMT 2020 can do all of these things extremely well. So energy efficiency is increased by 100-fold, connection density, latency, the usual kind of things in here. We've got a nice sort of light green area in the middle here that, well, it says here it says here IMT advanced, which of course LTE advanced is the is the technology associated with that. So you can see it falls short in a few areas. It doesn't do too bad, you see, when we look at areas like spectrum efficiency and even something like the perceived, the user data rate. But it falls short a little bit in terms of overall area traffic capacity and energy efficiency. And we're kind of getting there with the latency, with some of the latest issues. But I mean, these are the areas of development. More to do with the radio access than maybe what goes on in the core network. So, how can we build a new radio interface? What should the physical layer look like? Arrangement of base stations, that kind of thing. That's when you get to these, where you're able to extend that light green area in the middle to meet what the IMT 2020 KPIs seem to be saying. Now, of course, we're on a timeline as far as development is concerned. Won't worry about this one too much, except that we're sort of part of the way through 2017 now. We've done a little bit in terms of spectrum. I'll mention that in a moment or two. Recently this year, some technical performance requirements have been issued by the ITU. There's an important thing coming up soon. This WRC 19, where there'll be more to do with network sharing and spectrum availability of spectrum and such like. But I think once we get into 2018-19, this is when we're going to start seeing some proposals, and I think maybe some initial specifications will begin to be thrown around, both in the radio access network and in the core network as well. But of course, we'll probably have to wait until 2019 or thereabouts before we start seeing any serious technical specifications coming out of the likes of 3GPP, detailed IMT 2020 radio specifications and such like. It'd be interesting when we do get to that point to see exactly how they've solved a lot of these problems. I mean, rest assured that all of the big vendors and chipset vendors out there are running quite detailed R&D trials at the moment and are publishing quite impressive results in terms of what their network speed and latencies and power efficiencies are. But of course, their R&D at the moment, they're not, the technology hasn't been miniaturized, it hasn't been ratified into a full standard at the moment. It's quite interesting to see what's happening in other parts of the world as well. I mean, Verizon in the US, for example, I mean, they seem to have their own version of 5G, which is brewing at the moment. So Verizon and Qualcomm are kind of working together to create a version of 5G. It'd be interesting to see how much traction that gains and whether or not it will even be launched before the sort of theoretical 2020 date. For those services, and I suppose the really interesting question is that if they do successfully manage to launch a 5G service before the 2020 date, just how compatible or compliant will it be with the standards body's version of 5G? But we'll have to sit and wait and see on that. Right. Well, of course, we're talking about 5G, but we probably should have a quick look over our shoulder and look at the current development on the 4G side or the 4.5G side, because of course the development doesn't stop here. Release 8 was when we found LTE, and release 10 and beyond is LTE Advanced, and more recently into release 13-14 we've got this LTE Advanced Pro, which is bringing the data rate up to about 3 gigabits per second and bringing the latency down to around about 3 milliseconds. So we're kind of getting there in terms of overall performance. When release 15 or release 15-16 comes out, so around about 2019-2020, well, I think there's two things going to happen here. I mean, I've got a couple of questions on this slide, really. What's the compatibility going to be between the 5G thing that comes out and the existing LTE thing? Is there going to be some forward compatibility built into the LTE standards? Will there be backwards compatibility built into the 5G standards? How are we going to integrate one network technology to the other? So I think that's something which clearly is going to be addressed by the standards bodies, but it's interesting to think about that as well. I guess this question is, is LTE going to evolve into 5G, or will LTE continue, much like 3G has done, as sort of almost like an independent roadmap where it continues to evolve into something better and faster until eventually 5G becomes the dominant standard? I mean, that's more or less how the 3G and the 4G standards are playing out at the moment. But as I say, we're going to have to wait and see for that one. There are some thoughts. I mean, this again is from the NGMN white paper, which I highly recommend you click and download it at the end of this presentation and have a read of it. It's very useful. There's a couple of thoughts in that document about how we might provide some interoperability, and the option one here is to concentrate first of all on a new radio access technology, but interconnect it with a legacy core network. I mean, that's fine. I mean, because in the end, what we'll be doing in the radio access network is delivering into and out of the radio access network. We'll just be delivering IP packets one way or another. That will be one way of thinking of it, I suppose. But it does mean that you're kind of held back by the limitations of the core network. The second option would be, of course, to deliver the new radio access technology, but of course connected into a new 5G core, and that gives you full network slicing and configurability, provisionability in the network, and is of course a much more complicated thing to do, and where you've got interoperability requirements between the existing 4G and 5G, so handovers, for example, then of course you've got to start thinking about the inter-core network operability between the existing or the legacy EPC and the new 5G network. I mean, again, rest assured, the new 5G network will have interoperability features built into it. We're not just going to abandon and forget the 4G thing altogether. Again, much like we've done with the 4G backward compatible, or at least interworkable with 3G. I think this may be more of a timeline than you're not just going to pick one of these options and do it. It's going to be much more of a timeline thing. And I think probably one of the hardest problems to solve is what goes on in the radio access network. So we may start off with, or the early deployments of 5G may look like option 1, and eventually we'll get to option 2, and finally we'll get to option 3, where you've got a fully interconnected network, including things like fixed networks and Wi-Fi. But the 5G core network now has interoperability with the existing or the legacy radio access, as well as the new radio access as well. So of course, it's clear there's pros and cons in all those cases. I think as you go from option 1 through option 3, simply the complexity, maybe the cost of the network will be much higher. But of course, in that complexity, what you're gaining back is much deeper levels of control over the network. So well, the radio network. Things that we need to think about in terms of designing the radio network, or the new radio network standards. We've got to be very cognizant, I think, of spectrum efficiency. I mean, the big problem to solve, first of all, is finding spectrum in the first place, and finding spectrum with the right properties in terms of its availability, its the amount of bandwidth that you can create from that, but also the cost of it as well. Something that's going to be important in terms of overall efficiency, things like self-organizing functions, multi-rack coordination, is going to be an important aspect of this. We see a little bit of this with the well, it's not really a legacy system at the moment, but within the LTE Advanced standard, we've got things like coordinated multipoint that begins to think about coordination of resourcing between multiple base stations, and of course we can extend that to multiple spectrum bands and maybe even multiple radio access technologies as well. And again, thinking about efficiency, massive MIMO, well, there's coordinated multipoint here, and then some other suggestions like non-orthogonal use of the radio interface. This is one of the ways that we can lead to greater and greater spectral efficiencies. There may be some aspects of dynamic topology in here as well, moving cells, relays, hubs, and there's sort of discrete RANs and cloud RANs. Also device to device, I think that's important for things like vehicle to vehicle, for example, and some public safety applications. Those are things that need to be thought about in constructing a new physical layer or new physical layers, as it's probably going to be. If we just skip to the core network now I've deliberately put a kind of complicated looking picture up here. This actually, and again, I haven't included the link to this particular document, but it's worth doing a quick Google and finding the 5G PPP, because they've got quite a lot of detailed white papers on different use cases and so on. One of them is their view on architecture, which is where I've borrowed this picture from. But it does give you the impression of this sort of a layered application or layered processes or functions within the network, and sitting right at the top of this stack, if you like, is the applications and the business services. So if you are a connected vertical, so if you're a vehicle company or a smart city operator, then you kind of sit in this region, and you've got to start thinking about how you might interconnect with the communication provider. And the communication provider really is everything below this line. So if we draw a line right across here, then you've really got the user of the service sitting up here, and then you've got the operator, if you like. Remember that term, network as a service. So it's how do we solve those particular problems? And as always, interesting, these lines, these vertical lines that we see between the infrastructure operator and the outside world. I mean, these, of course, would be APIs of one type or another, application programming interfaces. So a lot of thought is going to have to go into what those APIs might look like and how easy or difficult it will be for those users of the service, the applications and the IoT providers, how easily can they interconnect and configure the network operator's system for their specific application. And because there will be a heavy reliance on things like virtualized functions and software-defined networks, which really control what go on down at this level. So in our connectivity layers, large use of NFV and SDN to control access to network functions and provision the required service right across the network. At least in 5G, every node in the system, including the user device, the base stations, switches, routers, and such like, every device is considered to be a configurable component in the creation of a network slice. Now, so it's a deliberately complicated picture, which we don't really have time to talk about in much detail. But I think whenever you start looking for, how does a 5G network work or 5G network architecture, the thing that always comes, ranked at the top of the search lists is network slicing. Okay. Now, the idea behind network slicing is that you can have shall we say, a common off-the-shelf, data center kind of environment with access to mobile services. So you've clearly got some sort of radio access technology in here. It doesn't have to be radio access. It could be fixed access as well. But understanding what the specific communication requirements of a particular application is. So we've got a couple of examples here. We've got smartphones, we've got autonomous driving, massive IoT, and then maybe some other examples sitting in the bottom there. So if it's just, mobile broadband, then there's a particular configuration that you need. So you need this kind of control plane, you need this access to capacity on the user plane, you need to understand these things about the users, or you need to configure the devices in a particular way. Then all of those different configurable metrics, well, they might be very different when you consider things like vehicle-based communication. So, telematics for the vehicles, if you want to change the engine map, if you want to improve the performance, if you want to get driving data being reported back. Well, again, those will require different communication services actually in the core of the network. And to keep the cost down as well, I mean, you've got to think about, if there's going to be, 60 to 100 million new cars on the road, over the next few years, with 4G or 5G modems in them, what services should those modems provide? And it would be a hell of a lot cheaper if we could just have some sort of generic modem that we put into all of the devices, and at the time at which the service is required to be provisioned, we could configure specific radio interface, specific power levels on that device. And that configuration should be allowed to be done over the air. So at the back end of the system here, where you've got, should we say, an IoT connected vertical, well, that connected vertical will clearly know about the specific application and what all of the KPI requirements would be of that service. And maybe the job of the mobile provider then to decompose that requirement and configure all of the necessary equipment in the network, maybe even including the end user device, whether it's a modem in the vehicle, whether it's a smartphone, a smart meter, whatever that might be. But really, this whole idea of network slicing is a sort of key area within the 5G standards process. I think Nokia, Siemens, Ericsson, and one or two others have been doing some fairly advanced trials using this. But the key to being able to do this is support for this idea of network function virtualization and also software-defined networking. Now, operators, to one degree or another, have got something like NFV, SDN in the network at the moment, but maybe not to the scale, and certainly not to the capability that we would require to build a 5G network. Now, as I mentioned before, a big thing, of course, for 5G is finding the spectrum for it. I mean, given these massive data rates we're talking about, 300 megabits per second, gigabit per second, whatever that might be, just how much spectrum do you need? What kind of channel bandwidth do you need for that? To support those services, and where are you going to find that amount of spectrum? Now, this is again another ITU document, this 2290, It's a bit of an old document now, but there's still some interesting information in there. The conclusion of that document basically is that when you consider the highest levels of prediction in terms of data usage, we were going to need approximately 2 gigahertz or 2,000 megahertz of spectrum. Okay, now that's nothing to do with the band here. That's just the total volume of spectrum that we would need to meet all of the data communication requirements of all of the applications that we can think of around the world. So, I mean, that's the outside. That's right at the top end. It may not be as much as that, but we've got to go ahead and find, 2 gigahertz of spectrum, and much of that spectrum is already being used. For, of course, it's still these days for GSM, 3G, 4G. And so on, but we've got to find some additional spectrum. So the hunt is on at the moment for more spectrum, and we had recently 2015, so WRC 2015. We were able to find, if you like, or at least they were able to find a bit of spectrum still in our sort of UHF band. So there is some spectrum availability. We've got to think about it on a global basis as well. There's no point in you really just finding a funny little bit of spectrum that nobody's using at the moment. Well, there may be a reason that nobody's using it. Maybe it's not available in a harmonized way in all parts of the world. So that's one of the big problems, is finding sort of harmonized spectrum that will be readily available, maybe not immediately, but over the course of the next 5 years or so. Finding spectrum that most countries can agree upon that should be made available for maybe the initial launch of the 5G services. So the spectrum in and around about the 1400 megahertz band, not a lot of it there. There's more spectrum up and around about the 3600 to 4200 megahertz, depends specifically on the country, but these are the strongest candidates, shall we say, for an early launch of 5G networks. However, there isn't a lot of spectrum available there. So if we're trying to meet these gigabit per second per user targets, we clearly need more spectrum than that. But this will be for WRC 19. Well, it's either WRC 18 or 19. I'm not quite sure when the date would be. I've seen both of them being bandied around. I pulled down a document from Ofcom. Obviously, we're based in the UK. So this is just Ofcom's comment on spectrum from Europe. Now, this is coming out of work that they're doing with the Radio Spectrum Policy Group, sort of a European forum, if you like, for discussing spectrum. And sort of identifying, this is not just in the UK, but across Europe, that maybe some, low bandwidth spectrum in and around the 700 megahertz band. Now, that might be interesting for those low power, long range type applications. Obviously 700 megahertz, longer wavelength, better penetration through buildings, longer radio links and such like. That might be interesting, but it's low bandwidth. So you'd have to be looking at low capacity applications, and maybe there are some IoT applications that would benefit greatly from availability of spectrum in and around that band. Medium bandwidth in that sort of bit that was identified by WRC 15, so 3.4, 3.8 gigahertz. Maybe that's a primary band, so early 5G launches. And then when you want high capacity, then of course large bandwidth are required. So we're going to be looking much higher up the radio spectrum. Now there's a lot of investigation into those so-called millimeter wave bands. So now we're looking at wavelengths between about 1 millimeter and about 10 millimeters. So in fact, all the way up to about 60, 70 gigahertz of spectrum are being investigated. Now, obviously, when the radio wavelength gets that short, or the frequency gets that high, then you've got other challenges that need to be solved in terms of coverage area. But actually, some of the technologies being proposed for the 5G radio access, for example, massive MIMO, actually benefits from the millimeter wave band, because you can then build a slightly more manageable antenna, because the antenna elements will be very small. You can put a lot of them into a small infrastructure, and you can actually overcome some of the propagation deficits because of the high frequency by using very high gain antenna approaches. And that's really what the massive MIMO is about. It's more like a kind of like a beam forming technique in some senses. But that can overcome. I think it was it Docomo been doing trials with massive MIMO, and certainly these very high frequencies. I think it was around about sort of the 20 to 30 gigahertz band. using a massive MIMO array, they were still able to punch out to about 1500 meters at very, very high capacity. So again, we're looking at multiples of 100 megabits per second over about a kilometer and a half at very high frequencies. And that's really down to the antenna techniques that are being developed as a massive MIMO and the like. So there's a lot of really exciting stuff to come, I think, with 5G, particularly in the radio access. It'd be really interesting to see how they solve a lot of the problems, the diverse problems, given low power, long range, high speed, high capacity. It'd be interesting to see what comes out over the next couple of years. And interesting as well to look into the core network and to see how specifically we'll be able to create these so-called network slices and what that exposure of network service will look like towards the end users of the service, so the connected verticals, as we like to call them. Now that's about all we've got time for. I say there's